I've been teaching and tutoring math for over a quarter century, and I can give those skills over to you by watching today on High Peak Education. Curl is part of Stokes' theorem. So in the same way you use divergence calculation as part of the divergence theorem, you use curl as part of Stokes' theorem. What I'm saying is we have to understand the curl first before we can understand Stokes' theorem. So the curl of a vector field is going to be essentially how much the vector field rotates. So if you have a vector field that has rotation, axis of the curl is going to be pointing out of the screen. In other words, by the right-hand rule, you would calculate this curl, and the curl is going to point out of the screen. Now remember from electricity and magnetism, we had this thing where we do like a dot like this with a little circle around it, and that means out of the screen. We want to see how much rotation there is in terms of the vector field. So here's another nice example. This is of a three-dimensional vector field. So you see what this person is doing? Imagine you got some vector field like this going around counterclockwise if you view it from above. So if you're looking down the z-axis, it looks like it's rotating counterclockwise. So by the right-hand rule, we point our fingers in the counterclockwise direction. The thumb points upward. So this is going to be the direction of the cross product. So you could say this cross product is just the curl of the vector field F. But again, curl is also given by gradient vector cross product with the vector field. So they're just one and the same. In terms of line integrals though, we could say we're interested in how much curl there is along each surface. That's why we dot product the curl with the local normal vector. Because I could have one surface here that's really spinning like this. So that has a curl like this. But over here, if I have the same solid, so suppose this is a closed surface, but suppose over here, I've got this side, which is very slowly spinning, but instead of spinning clockwise, it's spinning counterclockwise. So then the curl, by the right-hand rule, my thumb points outward that way. So this would be, let's say, surface 2, and then, again, this is the direction of the curl. Remember, with Stokes' theorem, we have to have a closed surface. So here's one way to think about it. So if you add up all the small little green twists in the area, that's going to be adding up all the curls as a double integral, which, by the way, from Stokes' theorem, will be just the right-hand side of Stokes' theorem. So it's the double integral of del cross f dot n ds. So that's what we mean mathematically when we look at all these. But that should equal to the circulation around this closed curve. The outer circulation around the closed curve is the net spin of this vector field. And mathematically speaking, that's going to be the closed loop line integral of f dot dr. And here's the amazing thing about Stokes' theorem. Stokes' theorem says these two are equal. So Stokes' theorem is the bridge between these two. So the line integral about the boundary C is equal to the surface integral over the closed surface S. Especially if it's in 3 dimensions, the surface might look something like this. Notice the curve might be, say, just like a circle on the bottom, and the surface might actually be not like a flat surface. It might actually have some, 3-dimensional curvature to it. And then all the normal vectors, of course, always point outward normal. But the point we're getting at is, indeed, the idea of Stokes' theorem still holds for any closed surface bound by any closed curve.